All right, folks. Welcome back from lunch. Hope you enjoyed the food. My name is Pavel Pinchaha. I'm a professor at the University of Utah. And we're going to be kicking off here our session on numerics. Really exciting to have a numerics session at PLDI. It's growing in importance, and there's a lot of very cool work applying formal methods thinking, applying programming languages techniques to numerics. And we're going to have a lot of that highlighted today in the program. So the first talk is going to be by Chen, and she's going to be talking about using traditional optimization techniques to solve floating point constraints. So, Chen, please.
Yeah, thank you. Hello, everyone. I'm Chen from Nanjing University. Today, I'm going to talk about our work, solving floating point constraints with continuous optimization. Pure floating point constraint solvers are useful when verifying programs that perform exclusively floating point computations, such as numerical libraries or scientific and high-performance computing benchmarks. Existing solution methods primarily rely on SMT solvers. They integrate an SAT solver for handling the propositional structure of constraints alongside a specialized series solver. Despite their ability to cope with logical constraints across various series, their solving in the theory of floating point arithmetic remains a significant challenge. Along with disadvantages, for example, when the constraint is complex, they will generate large SAT problems, which are difficult to solve efficiently. Recently, a separate line of work emerged, approaching the problem from a new perspective. Specifically, it leverages mathematical optimization methods to find solutions to satisfiable floating point constraints. Take a work called XSET as an example. The key idea of XSET is to reduce the original constraint pi into a mathematical function R, such that finding values of x to satisfy pi is equivalent to finding values of x to achieve the global minimum of R. And they employ Monte Carlo Markov chain to solve the mathematical functions. XSET has proven to be both effective and efficient, outperforming existing SMT solvers like these three by a large margin. Despite the great success achieved by XSET, there remains plenty of room for improvement, including its translation rules and the mathematical optimization method, MCMC. MCMC relies on random sampling to explore the search space, resulting in lots of iterations to effectively sample from the entire space, and eventually leads to slow convergence to the target distribution. Driven by the shortcomings of XSET, we propose a new MO-based method. Our insight is that over the past decade, gradient descent has shown extraordinary capabilities in tackling complex optimization problems. For example, in deep learning, gradient descent is often used to minimize loss functions whose parameter size can scale to trillions. Thus, we want to employ gradient descent as the underlying MO method for solving the mathematical functions corresponding to the original constraints. This requires that the mathematical functions are continuously differentiable. So we design the translation rules to translate the floating point constraints into continuous mathematical functions. At the same time, we further simplify the generated functions to reduce the complexity of the function for the overall constraint. And evidence shows that the reduced complexity often improves the performance of MO method. Okay, now I'm going to use a constraint from SMT Computation 2024 to present the high-level workflow of our approach, so that everyone can get an intuitive impression of our method. Step 1. We construct an objective function from the given constraint according to the translation rules that we design. The rules will be further introduced later. For the first clause, a is less than or equal to b. Its objective function is presented in equation 1. We note that the function attains its global minimum, that is to say 0, only if the clause a is less than or equal to b holds. Otherwise, the function returns a positive number, indicating the clause has not been satisfied. For the second to the last clause, their objective functions are presented in equation 2 to 7, and the objective function for the entire constraint based on those individual functions for each clause is shown in equation 8. It requires the 7th clause to be satisfied at the same time when the entire constraint is satisfied. The capital F returns 0 if and only if all 7 individual functions evaluate to 0. Conversely, if any individual clause does not hold, its corresponding objective function returns a positive number, and consequently, the overall objective function f also returns a positive number. Step 2 is to solve the objective function, that is, to solve equation 8 for values of a, b, c, d, e, f, such that they can achieve the global minimum of f and thus satisfy the original constraint. Specifically, in this step, for each starting point, gradient descent first looks for a new set of values for all variables. For this example, after 2 iterations, gradient descent finds values that reach the global minimum. Then we validate the solution. First, we check whether the gradient of f at the current values of a to f is 0. If not, these values cannot attain the global minimum of f. Second, when the gradient is 0, we examine whether the value of f equals 0 under the current set values of a to f. If not, these values cannot be a model of the constraint. Third, when both gradient and the value of f is 0, we apply the current values of a to f to the original constraint to verify its correctness. Next, I'll give a detailed presentation of our MO-based solving methodology. As mentioned earlier, the key to a MO-based approach is to make the minimum value of the corresponding objective function correspond to the solution to the constraints. For this reason, the first rule when designing our objective function is to regard it as a metric for measuring how far the current set of value is from becoming a model of pi. The closer input values are to becoming a model, the smaller the value of objective function is. Secondly, we want the generated objective functions to be continuous and simple at the same time, so the gradient descent method can be applied to underlying solving and the complexity of the problem can be reduced. Firstly, for operations equal, less than or equal to, greater than or equal to, we define translation rules that generate exclusively piecewise linear objective functions. For less than and equal and greater than, we follow the intuition for less than or equal to and greater than or equal to. Specifically, we treat the strict inequality A is greater than B as a non-strict inequality A is greater than or equal to B plus epsilon. The epsilon is the minimum positive subnormal number according to IEEE 754 standard. The two inequalities are equivalent according to floating point semantics, and after such conversion, we can simply apply the translation rules for greater than or equal to derive that for greater than, to avoid possible errors caused by the finite precision of floating point representation. we shift the term, and the final translation rule for A is greater than B is to non-strictly compare A minus B and epsilon. For not equal, we use aforementioned rules for combination. For disjunction and conjunction of two constraints, we use multiplication and addition respectively to ensure that only one of the two constraints needs to be satisfied or both need to be satisfied. At the same time, since the first 5 rules we design are linear, the complexity of objective functions generated by subsequent combinations will also be alleviated. Now let's go through the translation procedure quickly. First, we represent the constraints as a parse tree and then use DFS to traverse it. Our solving procedure mainly consists of 4 components. We employ gradient descent with randomly selected starting points to solve the objective function. And when gradient descent returns a solution, we check its validity. It is necessary to check the validity of returned solutions due to some floating point intricacies. Only with the validation procedure can ensure the soundness of our approach. Now I will go through our validation process in detail. We first verify whether or not the gradient of the objective function exists. If not, we determine by returning the current solution or unknown, depending on whether the current values satisfy the constraint or not. On the other hand, if the gradient exists, we perform a 3-step validation mentioned before. First, we check if the gradient is 0. If it is not, the solution cannot be a global minimum of the objective function. Second, if gradient is 0, we check whether Rx attains 0. If not, x cannot be a model of the constraint. Third, when both gradient and function value are 0, we check whether x is a model of pi. This validation process not only ensures the soundness of our approach, but also improves the overall efficiency. We implement our method into a solver called Greater and select 6 other solvers to compare with, including MO-based solvers, fuzzing-based solver, and classic SMT solvers. And we use 2 benchmarks for evaluation, with our own benchmark focusing more on challenging floating point constraints. The first table shows the results of all evaluated solvers on JFS benchmarks. The right-hand side figure plots the time of each solver on each constraint. We can see that in terms of the time, the number of constraints solved, Greater, BitVuzla, and CVC5 ranks among the top. However, Greater demonstrates a higher efficiency than BitVuzla and CVC5. Compared to XSET and CoverMe, Greater is more effective and efficient. When exclude constraints that Greater can solve while XSET or CoverMe cannot, the advantage of Greater in solving time will be more obvious. Finally, JFS and these 3 are the least effective baselines, solving significantly fewer constraints but running much slower compared to Greater. Now we come to the results on our own benchmarks. This time, although the number of solved constraints for Greater is the same as that of BitVuzla and CVC5, the time it takes is much less, and Greater is also faster than all other solvers. To conclude, we introduce Greater, a mathematical optimization-based floating point constraint solver, and the main advantages of Greater over existing MO-based solver lie in the simplicity and the continuity of our translation rules and the effectiveness of a gradient-based MO method. And that's all for my talk. Thank you.
All right, so we're going to do questions. And do you want me to run it? Sure. Question?
Hi, I'm from State University of New York, South Korea. I'm the author of the XSAT that you just cited. And I'm very surprised that this paper have very mixed feelings because I do not understand the delta between this work and the XSAT work. If I understand correctly, the most biggest difference is that you use a different mathematical optimization backend. That is a gradient-based backend. And the original XSAT paper that it was using MCMC. A second question is, I'm also the... Okay.
So the difference between the two work lies in two parts, as I stated here. The gradient-based method is inside of our whole work, and in order to use the gradient descent, we design more simple and continuous translation rules so that the underlying method can be applied.
Okay. I'm going to try to make sure we can get many questions, but I will note that there's a more detailed ablation study in the paper. Are there other people who want to ask a question? Jay.
Hi, Jay Lim from Yale University. Great technique. I just want to, could you go back to page 11 really quickly? I have a question regarding that.
Okay.
Nothing too big. I was just wondering, how did you pick the epsilon? Do you pick epsilon based on the size of A and B, or?
It's
just a small value.
It is a set.
Small is possible to normalize value, I would assume. Okay. Yeah. Okay. Well, one just quick note is it might be the case where, because epsilon is so small, like b minus a plus epsilon, the epsilon might disappear due to rounding error. So maybe it might be something you might want to look into. I don't know.
Sorry, I don't understand.
Oh, I see. We can talk later.
Oh, okay.
Great.
Okay.
Yeah. Yeah. Often better to go into detail offline. Other questions? There was one in the back. I'll take an opportunity to ask a question. So I assume the results depend on the initial value chosen?
Actually, for solvers that depend on the randomly generated starting point, we run each solver on each constraint like 10 times. So the impact of the starting points we think can be ignored.
Do you think it would be useful to use one of these machine learning frameworks like PyTorch to test many more initial conditions in parallel?
Maybe.
Okay. Let's give our speaker another round of applause. Thank you, Chen. And let's have our next speaker set up.